Hi, in this video I'm going to be going through the second task of the ISP for Unit 4 on further mechanics and electromagnetic fields. So in this task we're really looking at circular motion, not very much, I know we've done a substantial amount about that in class, but we're also looking at electric fields and really starting our work on electric fields. Okay, so let's get straight stuck into our explaining everything tasks on this. Right, so the first part of the explaining everything task is the idea of defining the term electric field and drawing a diagram of a radial and uniform electric field. So remember, an electric field is an area in which a charged particle experiences a force. Okay, so a charged particle experiences a force. That's the definition of an electric field. Remember, uniform electric fields. Let's draw them out. Okay, positive and negative. So the arrows always go in the direction of which a positive charge would move. Okay, so positive charge would move in that direction. That's a uniform electric field. That's a very poorly drawn one. Number one, because these are not equispaced, and secondly, because these are not drawn with rulers. So make sure you do that when you do this in your exam. So equispaced to show the uniform nature of it, and also draw all lines with rulers. Okay, so we've got two radial fields I'm going to draw. Again, remember, draw these with rulers, make sure they're equispaced, unlike mine. These lines are going out. Remember, the lines always show the direction that a positive charge would go, so that must be positive. If this is negative, the lines would go into it. Okay, like so. Okay, so it's a negative particle in the middle there. So that's a radial field there, they're radial fields, and that's uniform electric field. The second part of the task, pretty straightforward, is explaining how we can calculate the size of the centripetal force. Two main equations for this. There's two main equations for calculating the size of centripetal force. So F is equal to mv squared over r. Okay, that's the main one that we actually use in this situation. That allows us to figure out the force dependent upon the mass of the object, the velocity object, and the radius. Okay. The other idea is what the angular velocity equation. I'm going to show you where you can find these really easily, because I genuinely worry at times that students don't look at the equation list often enough when doing questions on this area, saying that I better forgot to put it in here. Let's have a look. Yep, I have forgotten to put it in this document. Let's see if I put it before the explaining everything task. No, I haven't. There you go. I'm not as bad as I thought I am. Okay, so remember, always look for the correct heading of mechanics, then look for the area, so circular motion or motion in circle, and then look for your equations. So you've got the idea of F equals mv squared over r, but you've also got this idea of A is equal to r omega squared. Well, hold on, we know that this comes from F equals ma. They tell us that over here. Okay. Well, if A is also equal to r omega squared, then surely we can just replace A with r omega squared. Okay, and we have another equation for circular motion. So we've got two equations for circular motion. One for angular velocity and one for normal linear velocity. They're the two main things that you need to get across in that explaining everything task. So I would write this equation out and define all of those, giving the units of each of them as well. Okay. Right, so let's quickly go on to task 2. Remember, my two videos are a bit quicker because there's a lot of content to cover. It is very reliant on you guys putting the work in yourself. So we've got an LCD display here. We've got molecules that are in this electric field. Okay, and they're saying on diagram A, it shows the forces acting on the molecule when the switch is closed. When the switch is closed, you can see how they are actually lined up. Okay, you've got to explain why the molecules actually align with the field. Oh, sorry, we've got to actually draw on to diagram A to show on diagram A show the forces. So if I move this out of the way, you can see the marks attached there. Yeah, so show the forces acting on the molecule as the switch is closed. As the switch is closed, you have got to draw what actually happened here. Okay, so remember, these are positive at one end and negative at the other. Okay, so remember, the smaller side of this is negative, so this is the negative side of the supply, that's the positive side of the supply. So in other words, they rotate in the clockwise direction, so positive is at the top and negative is at the bottom. Okay, that's the first part of the question. So, why are they actually aligning with the field? Well, the forces are not in the same line. So remember, for an object to be equilibrium, you've got to get these forces collinear. Okay, so we've got to get them lined up essentially. Otherwise, a turning force will be in effect. Okay, so if I draw that out over here, if I'm pulling from one side up and I'm pulling the other side down, okay, this will rotate until these forces are collinear. So in other words, you have a force acting up there and a force acting down there. So there will be a turning force or a torque or a moment, okay, until they're collinear. Okay, so that's the idea for this one here, for the second part of it. That's why that's the explanation of why it aligns with the field. Diagram B, draw field lines to demonstrate the electric field in the region of the plates. Okay, so remember when you're drawing electric field lines, you've got at least three field lines drawn, and it's going to be the correct direction. So it's from positive to negative. So the arrows point towards the negative side. So look back at the explaining everything task if you need help with that one. Calculate the strength of the electric field. Okay, so calculation of the strength of the electric field. Okay, so that's E equals V over D. Okay, so the idea, remember the definition, well, the unit of electric field strength is volts. Sorry, the unit of electric field strength is volts per meter. Okay, so we've got 1.5 volts. What the distance they are apart? Yep, that's that over there. So you end up with 1.5 times 10 to the 5 once you do that. Okay, so 1.5 times 10 to the 5 once you do that. Nice 7-mark question to get us going. Okay, question number 2. Again, so remember, feel free to pause the video and read through the question if you need to. But again, similar sort of things they're getting us to do. Sketch on a diagram, pattern electric field. So you've got to get the lines vertically down, the arrows pointing down. Okay, so you've got to get the vertical lines in there. So 3 generally is what we say, and they've got to be pointing down. Remember in the mark scheme, if you read carefully for this question, it says 2 or more. I've always suggested 3, so we should always do 3, and in the majority of questions suggest 3, and that's why I suggest 3. The arrow is down, remember, because it's from positive to negative. Top plate being positive, bottom plate being negative. So electric field strength again, says E equals V over D. So if you plug in your values, that's 2000 divided by 0.8 times 10 to the minus 2, times 10 to the minus 2 because it's centimetres. Okay, so you end up with 250,000 essentially. So 250,000. That's what we end up with. Okay, so 250,000. So the sphere has a mass. So this is one I'm going to go through a bit more detail. Sphere has a mass. During one experiment, it has an acceleration upwards of 3 times 10 to the minus 7 meters per second squared. So we've got an acceleration, we've got a mass, so we can calculate force, we know that straight away. Calculate the magnitude of the charge on the sphere and state its sign. Well, we've got to figure out this force that's actually causing this acceleration. So remember, if there's a force that's causing the acceleration, we can use F equals ma. But that force is due to the charged particle being in an electric field. So we've got another equation for forces for charged particle and electric fields, and that is essentially F equals E over Q. Sorry, E times by Q. Well, if the only force acting is that, which it is in this situation, then surely we can equate them. So EQ is equal to MA. Okay, so we've got M and A, so we can figure that out. And we've got E, and they want Q. So therefore, Q is going to be equal to MA over E. Okay, remember the E is that 250,000 value that we had from before. Okay, so this is going to be a really small charge, and that's right. Okay, this is a small charge particle. It's going to be very, very small. So remember, as soon as they've given us the charge of a particle, they can say, well, how many electrons would that be? And therefore, we just need to divide by the charge of an electron. I don't think they asked that in this question, if I remember correctly, but they can ask that. Okay. So I'll go through this calculation just to make sure you're happy with this one. So it's 1.8 times 10 to the minus 7 multiplied by 3 times 10 to the minus 7. So that's the top line. That's the mass times the acceleration. So that's our force essentially. Well, we need to divide that by electric field strength. So it's 250,000. Okay, so 2.16 times 10 to the minus 19. So it's just over the charge of an electron. Okay. 2.16 times 10 to the minus 19. A very, very nice 4-mark question to get. A lot of people trip on that, but that's pretty straightforward. Remember, the unit is coulombs, needs to be a capital C. Explain what is important for the experiment to carry out in a vacuum, because any other air molecules in there, any other gas particles would provide other forces and it could collide with the sphere that's actually in there, so we won't be able to actually take decent measurements. It's a 9-mark question there. So that covers ISP task 2. I know that was quite quick, but there's 2 big questions in there and 2 very tricky questions in there, so make sure you go through that again if you need to. So thank you very much for watching, guys.